Okay, I want to solve this one. It looks more interesting than other two. And then I'll probably take a break and try to figure out how to fix my drawing because this is unusable. Okay, so in this problem we have some infinite chessboard. It's two-dimensional, and we have some interesting figure which have some number of moves. It has n pairs of numbers a, b, and it can move move by the vector of ab or minus a minus b. So from square xy, it can move to the square x plus a y plus b, or x minus a y minus b. And the statement says that two knights are equivalent if they can from equal starting positions they can move to the equal sets of squares, and the statement says that for each knight, this figure, there are equivalent knight which have n, the number of different vectors, equal to 2. There is also some info about somewhere said that not all the squares the knight can visit are collinear, so not all of them lies on the same line, but I don't think that it's very important. Well, maybe it is. So A's and B's are up to 100. That's interesting. It's not very big number, and we want we have to find this equivalent knight with only 2 different moves. So so the set of squares we can go to is linear combinations with integer coefficients of our starting vectors. We are starting from 0, 0, and then we can do for example 5 moves with one vector and minus 3 moves with the other. Minus 1 move means that we go to the opposite direction, using this option to go to x minus a and y minus b. So in the end we will end up in the position 5 times first vector minus 3 times the second vector. And basically we are given some set of vectors, and we want to construct in some sense integer basis of all the set of squares that are reachable from 0, 0. Okay, let's use it. They're not linear. What do I want to do? This is just doing some crazy shit. Okay, fine. I'm happy with that. So we have starting position. Let's say that we have some two vectors which are not collinear. So this is x1, y1, and x2. Wait. Let's take this vector with coefficient y2 and this with coefficient minus y1 and take their sum. It's easy to see that the second coordinate will be 0. y1 times y2 plus y2 times minus y1, it's 0. And the first will be x1, y2 minus x2, y1. So if we can go to some point, some square, we can just add this vector to our set of moves we can do, and it won't change actually the set of reachable cells, because like we can, if we want to do this move, we can just do some linear combination, like this linear combination of these two moves, and it will be the same. So from this we can get that we can move horizontally. Okay. Maybe that's not like the best thing we can get. For example, if these two numbers were not coprime, like they had some common divisor greater than 1, we can divide both this coefficient by the common divisor, and this number will get smaller. So we can move horizontally. In the same way we can move vertically, but it doesn't mean that like, obviously we want to find the smallest move horizontally and the smallest move vertically, but it doesn't mean that it will be enough. For example, if we have like two diagonal moves like this, like 1, 1 and minus 1, 1, the best we can do for horizontal and vertical moves are like 2, 0 and 0, 2, but using these two moves we cannot reach 0.11. But what we can do is we can find the smallest positive y coordinate that we can go to. How do we do this? Well, we can just ignore x coordinates, and then we just want to find the linear combination with integer coefficients of y coordinates of our moves, such that we will get something positive and as small as possible. Well, and I state that this number is actually the greatest common divisor of all the y coordinates of moves. It's kind of obvious that we cannot get any smaller, because everything we get will be divisible by the greatest common divisor, and like the things that we can actually get exactly greatest common divisor, it's like known fact. It's one of the great properties of GCD, that GCD of some set of numbers, it's the smallest positive numbers that can be represented as what did I want to say? The smallest positive numbers that can be represented as a linear combination of this set with integer coefficients. I won't prove it. Like it can be done. Like you should. Okay, we will kind of prove it constructively. We will get a construction that does it. It uses extended Euclid algorithm. So what does it give us? Like, if we will find the smallest horizontal move and the move with positive but smallest change in y coordinate, then I state that this is our answer. These two moves actually will generate all possible moves, like all possible sequence moves, all possible reachable cells. Why is that? Well, again, it's obvious that we cannot get any y coordinates that are not divisible by GCD. So, like, how to move from 0, 0 to some coordinate? We will just use our move that changes y's and use it so many times that we will get to the right number of y. It is possible, like the number of moves will be integer, because obviously this y should be divisible by GCD. And then we'll move as close as possible to our target point using horizontal moves. I state that we will actually get to this point. Why? Why is that? Let's say we want to go to some point, and our shortest horizontal move has length L, but we cannot get here. Why? Because like the point we will come to some point, for example here, and then we can change our x coordinate by L. And it can happen that the reminders modulo L of this and these 2 points, like of this of their x coordinates, are different. And if that's what's happened, we can't move from this point to this point. But let's go to the closest point we can. This distance will be strictly less than L. Some distance d, which is strictly less than L. Well, then we can reverse all the moves to get from here to here, and then make a sequence of moves to get from here to here, which should be possible. Like by doing all this together, we will move like from here to from here to 0, 0, and then to here, thus moving on the distance d horizontally, which is smaller than L, and it shouldn't be possible, right? So we get a contradiction. So what we want to do, we want to find like the smallest distance L that we can travel along the horizontal axis, and some move which has y equal to GCD of all the y's. Okay. I kinda know how to do the second. We should just do extended Euclid algorithm and do some hacks so that we cannot, so we won't get really big coefficients. Or maybe we shouldn't. Maybe we just want to get really big coefficients. Yeah, that seems right. Or maybe not. Okay. I still have to think about how do we get like, the smallest horizontal move. So we can get some. We can, for example, get this from all unsquared pairs of moves and get the GCD, but I'm not sure that it is actually the answer. Oh, okay, I have an idea. So we can firstly find the move that minimizes like get the y coordinate equal to GCD of all y coordinates. For this, like we will construct this move for like prefixes of our all possible moves. For one move, it's just this move, because GCD of set of one number is just this move. Well, it could be bad if it has 0, but it's kind of fine. Like if there are no moves that can change y coordinates, we will say that it's 0. And suppose we had for some prefix, we want to add the next possible move. So we calculate the GCD of like our previous GCD and new y. This way, like using extended Euclid's algorithm, we will get coefficients with which we should take our previous moves to get this one new. The problem is the x value of this move, the x coordinate, can become really big, but we can at first find some horizontal move. It should exist, so it will have not very big x coordinate, 2 times 10 to the 4th, maybe. And we can always take our x coordinate, which we will get modulo this number. Like we will again get a valid move with the same y coordinate, which is the only thing we care about. So in the end, we will get a move which has y coordinate equal to GCD of all y coordinates and some x coordinates, which is not very big. Then we will do this thing. Like, suppose we had some move initially, and now we have some move with the y equal to GCD of all y's. Then we can repeat this move such that y coordinate will be equal to y coordinate of this first move. Then we can take difference of x coordinates, and like this is the horizontal move which should be in our should be possible, because it's obviously possible to do this move, and it's possible to do our sequence of moves, so the difference is also possible. And like this way we can get some horizontal moves which are all possible. Then we can do the same thing which is like which we have done for y coordinates, and get from this set of moves the move with the smallest x coordinate, which is equal to GCD of all the others. It will obviously have y coordinate equal to 0, because all of these moves were horizontal, like all of their linear combinations are also horizontal. And I say that this move, like, it is possible because it's a linear combination of some moves, and this move is enough to generate all the starting moves. How? Like we will use our like master move with y coordinate equal to GCD, repeat it the number of times we want. Like we will get the difference, which is divisible by our GCD, like in x coordinate master move, and we will repeat this move the required number of times. So we can get each starting move, and so each starting move is a linear combination with integer coefficients of our two moves, and there is why it's also like all of the linear combinations with integer coefficients of starting moves are the linear combination of our two moves. So this is the full solution. I will repeat once more. We want to find master move with the smallest possible y coordinate, which will be equal to GCD of all the y coordinates from starting moves. Then using this master move, we will generate the set of needed horizontal moves, needed and possible horizontal moves. Then we will repeat the same for this thing. For horizontal moves, we will get the master horizontal move, and these two moves are the answer. So let's go. We will just need extend Euclid algorithm, text numbers, return the GCD, and also two coefficients k and l such that k times x plus l times y is the GCD. If y is 0, then GCD is x, and we can just say that k is 1, l is 0, and GCD is x. X times 1 plus y times 0 is x. So I will start. And otherwise, we will have recursive call. You can see that I have switched the order of L and K, because L is the coefficient before Y and K is the coefficient before like x mod Y, which is actually x minus Y times x divided by Y. So we can okay, I'll write it. This is just extended Euclid algorithms. So we get G equal to. Okay, for some reason I can use my touchpad, but I cannot use my graphic sheet. I don't know. This is bad. So it's k times x mod y. I also cannot really draw with my touchpad. Plus L times y. So now we want to get x from here. Like we want to get this G is as linear combination of x and y, not x mod y and y. To do this, we will rewrite this thing as x minus x divided by y, rounded down, multiplied by y. This is the same thing by definition. And then we can like open brackets, multiply k by x, multiply k by this thing, and we will get k x plus L minus k x divided by y multiplied by y. And this is still g, which is GCD of x and y. So we want to get these two coefficients. This is why I swapped these two. So k is already a coefficient before x, and we should just do L minus equal k times x divided by y and return g. So we have some start moves. We will have y and okay, let's say that xy will be our master move for y's, and x2 will be our master move for horizontal moves. But first we should set x2 to some not very long horizontal move, such that if this x will become really big, we can just take modulo x2 and it will be fine. So we have moves. Just want to find a pair which is not linear. We just I have the formula somewhere here. We will say this. And if it's not 0, we want to find something non-zero. After this, it should be non-zero. Let's take modulo, because it's more convenient that way. So now we want to create master move for y. For now, our master move is just 0, 0. And we want to add all of our starting moves. We want to do if lead on this. So G is GCD. Well, actually, we want to do if lead on non-negative numbers. So we will say this, and if it was actually negative, we will multiply L by -1. So now GCD is non-negative. So K times our old move plus L times this new move will have y coordinate equal to G. So its x coordinate will be old x times k plus new x times l. It will be equal to g, and we want to take x modulo x2, so it won't become very big. So we have found our master move, and now we will do the same thing, but with only horizontal moves. So we want to generate all these horizontal moves. How do we do this? So we know that for all moves, its y coordinate is divisible by our y. So the x we want to create is actually the x coordinate of well, for example, like we have to repeat our master move for some k times. So if we do this, its x coordinate becomes k multiplied by x, and we need to subtract x coordinate, like takes difference between new move and old, and k is actually this number. How many times we have to repeat this move so that y coordinate becomes equal to this number. Again, let's take absolute value, and x2 is just GCD of all x2 and x, and we have to use some variables here. We don't need them, but we have to use them. That's all. Well, that's the answer, but it could have big coordinates, I suppose. I don't really know what to do with that. Okay, it could have coordinates up to 2 times 10,000, like 20,000. Okay, let's submit this. I have some idea. For submission check, obvious. It doesn't work. Great. Yep, we should stop if it's non-zero, so we should continue if it's still 0. Well, yeah, I guess that's like kind of the same as this. So we can submit. I don't think that it will pass all the tests, but it can. Oh, it did. Well, what we could do even didn't work. So like, what's the problem? The problem is that like okay, like y is obviously small. It's not greater than 100 because it's just GCD. But like x2 here can be up to 20,000. Like it's 100 times 100 plus 100 times 100 times 100. So after we do this, x is less than x2 by absolute value, but it still can be big. When we do this, like, x2 is well, it's obviously not greater than what we get here because this divides this value, obviously. But it still can be big, I think. Like 20,000 big. Not big, but a bit bigger than we are allowed. Okay. First of all, using this horizontal move, we can do the thing that this move is actually okay. The x-coordinate is in these boundaries. How to do this? Well, the length of this segment is like 20,000 plus 1, so we could just adjust. Like, it could be bigger by absolute value, but we can change the sign and it could be fine. But it could actually happen that maybe I don't really know, but it looks like it can happen that there is actually no horizontal move with lengths in these boundaries. But after we have done this, like this move is now okay, I think we can like adjust this move. Like do change the move by adding this move multiplied by something integer. It will be still valid solution because we can like using this move back, we can get this one back, and it's still valid solution then. And it might work and might not. I don't know. Well, okay. Maybe it's not possible to construct such tests. Maybe it's not, but I don't know. So, okay, I will stop here for now and try to understand how to get this thing working. And then I'll move to remaining two problems. Maybe not today, maybe today. So thanks for watching.